This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So it's just scrolling up and down.
Right.
Yep.
Thank you so much. All right. Well, good afternoon. My name is Gary Brown. And I don't know why this is going to be problematic, probably. I'm filling in for Nick Hutchins, yes, Professor Nick Hutchins. I was formerly chair of the department at Princeton University. And so what I'm going to talk to you about is gas dynamics. And so it's over a period, I think, of 6 weeks for 3 lectures a week. And up there, oh, you can't see that, can you? How do I...
Blow it up a bit.
How do we make that?
Hopefully it's not blowing up like the method.
Yeah, there we are. Is that... can you see that? You still can't see it? Okay. Then it's got to be even bigger.
There you go.
How's that? It's, I hope you can read it, because what I'm going to do is I'm going to motivate what we're going to talk about, and I'm going to start today with some things that are sort of background in a way. So today is for you to relax. You should know most of what I'm going to do. Here is a reminder for all of you, and these charts are going to be made available to you on the internet. These lectures, the first is today on a Monday at nominally 5:15 to 6:15, and it's in Redmond Barry. Wednesday is also 5:15 to 6:15 in the Copeland Theatre. And Thursday is in the morning at 11 a.m. from 11 until 12, and it's in the Harold Woodruff Theatre in the old microbiology building. And the texts that I think are very helpful for the subject, broadly speaking, compressible flow, they are Liebman and Roshko, and I was a great colleague of both of them. Batchelor, George Batchelor, G.K. Batchelor, has written a book about fluid mechanics in general, a very helpful book. And then there's a book on fluid dynamics by Landau and Lifshitz, which is a very good book. Landau was a very, very capable man. And there's a book on compressible fluid dynamics by Thomson, and quite a lot of what I'm going to do is not very far from what Thomson has to say. So today we're going to start with some background, because I don't think you can begin to understand compressible gas dynamics unless you know some thermodynamics. So we're going to do some revision of thermodynamics, and I've got some references here for you. There's a wonderful book by Sommerfeld, the great physicist, really, German physicist, called Thermodynamics and Statistical Mechanics. We're not going to say anything about statistical mechanics. There's an excellent little book of his lectures by Fermi. Fermi, as you probably know, was at Chicago, and one of the great physicists of the last century. Profound experiment that he did on fusion, which was the basis really for the development of the atomic bomb. Szymanski is a physicist, and that's a very good book, Heat and Thermodynamics. And then Reynolds at Stanford has a book on thermodynamics as well. So they're references, and references for gas dynamics. There's a very good book by Shapiro, Dynamics and Thermodynamics of Compressible Flow. Shapiro was at MIT. And there is a book that's an old book, an early book in a way, called The Theory of Sound by Lord Rayleigh. Wonderful volume. And then there's the Russians were very interested in shock waves, and they developed, as you know, the nuclear capability, and that drove a lot of their interest in the physics of shock waves. And Zeldovich and Reiser were physicists, and they've written a book on physics of shock waves and high temperature hydrodynamic phenomena. And it was very much influenced by the Russian development of their own, ultimately their own hydrogen bomb. And there's a wonderful book by Jerry Whittam called Linear and Nonlinear Waves. And I may have to say something about that. That's another wonderful textbook. And then if you are interested in the basic equations and tables and charts for compressible flow, there's an old NACA report number 1135, which has those equations and tables for compressible flow. Now I thought I would begin today talking a little by way of introduction really. Why is this all interesting, and what's happened and when? And I think it's always interesting to look at an historical perspective. Where have we been in the development of an understanding of heat machines? And they're of course based on fluid mechanics. So if we look at the Greeks and the Romans from 600 BC to 400 AD, what did they do? Well, one of the most important contributions was Archimedes. The upthrust of a floating body is equal to the weight of the floating body. He was the one who stated that. And hydrostatics is indeed based on his observations. And of course he developed the Archimedean screw, which became very important for irrigation and water supply, and indeed for mining, so that they could pump the water out of the mine. And then there was a Persian wheel in this period, and the Persians had pots on a rope and chain, but it was rotated. The pots were rotated through the water, and the water was lifted up in these pots on a rope chain, and it was rotated by a treadmill with human power, that is, or with animal power. Then, of course, the big advance came with the Greek water mill, and indeed the Norse water mill, but it was typically a vertical axis machine and relied on the water turning the mill, and typically it was providing about a half a horsepower. That was the power available. Then came the Romans, and in AD 180 they had developed the Vitruvian mill, and that was the first machine with gearing to transmit power, so it actually had a lantern gear. And it was an undershot wheel. That means that the water flowed underneath the wheel rather than the Greek water mill, which was a vertical shaft. So this was a horizontal shaft, an undershot wheel, and they were able to generate about 3 horsepower. Later, of course, and they were on quite a huge scale, they developed mills that were ultimately 6 feet in diameter, and they were absorbing 50 horsepower. So there's quite a lot of energy in the water. And then there were piston pumps, and the Greek temples were actually opened by something like a pump. They provided a weight on one side, and then they heated water to make it steam, and the steam pushed the door open, and then when they wanted to close the door, they put cold water on the steam, and then atmospheric pressure closed the door. So that was in some ways the early precursor, and it's hard to imagine that it took nearly 2,000 years until we had the first heat engine. Then I think from AD 400 to 1500, typically that is described by historians as the Dark Ages, and it includes, of course, the Renaissance. The Domesday Book was written in 1086, and it describes the southern part of England where water mills, there were 5,000 water mills distributed across the southern part of England. So water mills were the basic mechanical device, if you like, plus clocks. Clocks were developed in this time. The Dutch had windmills, substantial windmills in Holland. And of course, in this period, just at about 1500, it was Leonardo. This was the beginnings of modern mechanics in a way. Leonardo was a great observer. He was a wonderful engineer. You would know that amongst the many things that he did was to develop military ideas. Catapults were something that he did quite a lot about. And he had the first sketches of flight, 1500 AD. So now we're talking about the 17th century, and this is 1600 AD. And in this period, from 1600 to 1700, was the discovery by Torricelli, the first discovery that the atmosphere had pressure. And it was done by measuring the pressure at the bottom of a mountain and measuring the pressure at the top of a mountain. And it was the beginnings of the mercury barometer. And Pascal in 1647, Pascal's principle, which is that the pressure in a fluid at rest, the pressure acts equally in all directions. That was Pascal in 1647 when he was only 24, about your age. And of course in that period also was the giant of our subject really, Isaac Newton. And he determined the foundations for mechanics. And there's a wonderful story. He founded really calculus. And there's a wonderful story which Feynman tells of the great physicist from the 20th century, of the lady who comes out of her car, and she's driving her car along the road, and she's pulled over by the policeman. and the policeman says to her, "Madam, you exceeded the speed limit. You were doing more than 30 miles an hour past a school." And she replied, "But officer, I haven't been traveling for an hour." That is the motivation and the insight for what calculus was to mechanics. Newton, 17th century. Then we have the 18th century, and we have Pitot. In 1732, the first measurements of the local velocity in a fluid. 1732 is not so long ago. Thousands of years of human activity before anybody could measure fluid velocity. The Romans couldn't do it. So Bernoulli was also in the 18th century, in 1738, and he wrote his treatise about hydrodynamics, and we're going to talk about the Bernoulli equation, not only the incompressible Bernoulli equation, which was what Bernoulli was talking about. We're going to do the compressible Bernoulli equation. But the Bernoulli equation was the introduction, really, of potential energy and kinetic energy for real in the Bernoulli equation. And the other great pioneers in our subject from the 18th century were Lagrange, Laplace, Euler. We're going to talk about the Euler equations, and of course Galileo. There's a famous remark from Galileo in which he said, "I had less difficulty comprehending the motions of the planets than I did of water before my very eyes." So in this period, in the 18th century, was the very first reliable heat engine, the Newcomen engine in 1712. It generated 6 horsepower and had an efficiency of 0.5%. 0.5%. It was also the beginning of the atmospheric steam engine, and the first atmospheric steam engine had a clearance between the piston and the cylinder of 1/2 inch. You can imagine how effective an automobile would be if the clearance between the cylinder and the piston were 1/2 inch. Then I think we come to the really incredible advance in 100 years of the Industrial Revolution. Steam power in 1750 to 1850. And I love the story of Isambard Kingdom Brunel. You should know his name. There's a statue to him in Paddington Station in London because he designed Paddington Station in London. But he has to his name 3 ships. He actually designed and launched the Great Western in 1837. And it was the first transatlantic ship, and it was 1,340 tons, significantly more than a sailing ship. It was a paddle ship, and the boiler pressure that he used for his steam engine was 5 psi, and the engine could generate about 750 horsepower. It's huge compared with the water mills that we've spoken about from the Romans. Then in only 8 years later, he launched the Great Britain. It was 3 times larger in size, or nearly, not quite, 3,400 tons. It was 15, he had a boiler pressure of 15 psi, and it was powered by 1,500 horsepower. Then came, I think, the first screw ship, which was the Great Eastern, and it was an all-iron ship, 21,000 tons. So this is some achievement for an engineer, to go from 1,340 tons to 21,000 tons in 22 years. The lifetime of one man, 22 years he did it. And that ship had a boiler pressure of 25 psi and a power, an installed power of 8,300 horsepower. 8,300 horsepower. How many horsepower do you think there are in the locomotives that go between Adelaide and Melbourne? Come on, you must have some idea. How many horsepower has the locomotive that pulls all of those carriages through the hills and all the way from Adelaide to Melbourne? How many horsepower does it have? 30? 300? 500? Raise your hand if you think you've got the answer. 3,000? 10,000? 15,000?
I was going to guess 10,000.
Well, there's somebody brave. Come on, where are the rest of you? You can't be asleep. How many? 5,000? That's about it. 3,000. 3,000. So here's a ship in the 1859 that had 8,300 horsepower. It's a steam engine. Now, the steam engine that drove the great advance of the Industrial Revolution was Watt's steam engine. When did he do it? 1769. What was his patent? Who knows? Come on, some of you must know.
Was it the flyball governor?
I think he may have done the flyball governor, but the real patent that he first patented was a separate condenser. So he had a condenser separate from the cylinder. He wasn't spraying water on the steam to condense it. And at this time was the first definition of horsepower. And what is it? Well, it's about 2/3 of the average power of about 2/3 of the power of the average horse. And that was determined from experiment. And the efficiency of Watt's engine, so 1769, what was the efficiency that he achieved? 2.7%. So for all that coal they were burning, only 2.7% of it was actually useful work. The rest was in the exhaust. Nevertheless, this is the way Britain actually could colonize the whole of India. And really why, to some extent, the British and Western democracies also dominated China, the Industrial Revolution. They had something that in India at the time of the British colonization, there was only bullock wagons. And here's this iron contraption on a couple of rails pulling more than 50 bullock wagons could have pulled. It must have been hugely significant. Okay. Now in 1884 was the first steam turbine, 1884, the Parsons steam turbine, and it generated 7.5 kilowatts. It's not much. You've got much more than 7.5 kilowatts in your automobile. We're going to talk about de Laval. He was Swedish. And we're going to talk about a Laval nozzle. And this was developed in Sweden for the Laval turbine in 1889. Dr. de Laval. Now we're getting much closer to modern times. We're going to talk about Navier. Navier was French, of course, and an engineer. Stokes, the great British mathematician. And Lord Kelvin, the great giant of the 19th century. We're going to talk about Kelvin in a minute. Lord Rayleigh, Horace Lamb. Horace Lamb, as you may know, was appointed the foundation chair at the University of Adelaide in mathematics and physics when he was 26. Not much older than any of you. Horace Lamb, and the first edition of his book in hydrodynamics was written in Adelaide, in Australia, in 1879. We have Clausius, which will be familiar to many of you, one of the great German physicists, pioneer in thermodynamics, and Helmholtz, another extraordinary man, extraordinary genius. Helmholtz was the one who thought about the sound coming out of an organ pipe and realized that coming out of that hole, that slit, was a fluid moving with one velocity and the air wasn't moving at all. And he was the one who said that's unstable. So that's the Kelvin-Helmholtz instability. And Helmholtz arrived at his ideas by thinking about organ pipes. Then we have the 20th century, and the giants of the subject that we're going to talk about include Prandtl, G.I. Taylor, Kármán, Theodor von Kármán. Kármán, as you know, was from Austria, and Landau from the Soviet Union. Prandtl, of course, was German. G.I. Taylor was English. And that was the... Prandtl is known for boundary layers. G.I. Taylor for all kinds of things, including gas dynamics. Kármán for high-speed flow and turbulence, and Landau really for high-speed flow. So now we're in the 20th century, and what do you know about the 20th century? Well, I hope you know exactly when the Wright brothers first flew. How many of you didn't know? Be honest. When was the first flight at Kitty Hawk? How many of you didn't know? Raise your hand. Good. Well, you're courageous.
That is 1921.
No, 1903. And the remarkable thing about the Wright brothers is that they designed and built not only the aircraft, but the engine. The engine was central. And how much power did the engine have? 3,000 horsepower? Of course not. 12 horsepower. At what speed? 900 RPM. How much did the engine weigh? 180 pounds, which is about 70 kilograms probably. Your weight. And the aircraft weighed 750 pounds. Now, it's only taken a short time from the beginning of the 20th century to the end, when we developed steam engines, not steam engines, diesel engines, diesel engines, heat engines, diesel engines with 40,000 horsepower. 40,000 out of a diesel engine. So you might have a diesel engine in your car which might have 70 horsepower, but we're talking about huge pistons in big 40,000 horsepower in a ship, and some ships are actually powered by a diesel engine. And then we have the shuttle, the incredible development of the shuttle for the launch to the moon. And if you haven't thought about it, you need to think about it. How did it work? What was the thrust of the main engine of the shuttle? The thrust of the main engine of the shuttle was 3 million pounds. How could it be so high? Why? What is the thrust due to? Come on, some of you must know. Why did the shuttle have a thrust of 3 million pounds? It came from the gas dynamics of the burnt fuel, and the fuel was a mixture of kerosene and oxygen, and it was burnt in a combustor at very high pressure, and the flow through the nozzle was just like we're going to talk about. It was a compressible flow, so it reached Mach 1 in the nozzle, expanded out to about Mach 7 as I recollect, and that's about the optimum, as we'll find out. Yes? Yes, some of it was hydrogen and also kerosene. Yes, it had the main engine. You're right, was hydrogen and oxygen, burning hydrogen and oxygen. But the fuel that was kerosene, actually no, I think on reflection it may have been the hydrogen. I'm not sure now. The shuttle engine burned the hydrogen and the oxygen together to pump the liquid oxygen and the liquid hydrogen into the combustor. And to do that, it required an engine that would produce 70,000 horsepower. 70,000 horsepower. So that shuttle engine was an enormous triumph. How do you generate, and we're going to talk about that, how do you generate such very, very large energies out of a rotating machine? And then, of course, just to close this out, we know that today steam turbines are used to generate the power that lights these rooms, and these steam turbines could be 500 megawatts. Huge power. 500 megawatts is 500,000 kilowatts. So you can see that that's more than 500,000, 700,000 or so horsepower. All right, so now we're going to begin for real, and I want to talk about thermodynamics. How many of you have already taken a course in thermodynamics? Raise your hand. How many of you have never taken a course in thermodynamics? Raise your hand. 1, 2. Only 2 have never taken a course in thermodynamics? Well, this will all be very familiar to you, except to those few of you who've never seen it before. Okay, the first thing that I want to talk about is what is the state of a system. And we're going to talk about, firstly, a homogeneous fluid. What's a homogeneous fluid? What is a homogeneous fluid, or what is not a homogeneous fluid? Yes?
The properties doesn't change?
The properties are uniform throughout the whole volume. So if I had water and steam, that is not a homogeneous fluid. Thermodynamics applies to water and steam, but we're going to have to talk about that because there's a phase change involved. A homogeneous fluid is all of one phase, and for a given amount of substance and a given pressure and volume, it is a statement of experimental fact that if you measure some thermometric property, like the temperature with, say, a thermometer, you always get the same temperature. Now, we haven't talked about temperature, but temperature is something that you have some feeling for, how hot something is. And we'll begin by using something like a thermocouple or a length of a column of mercury that is determined by how hot, because the column of mercury expands or contracts with temperature. So the state of a system in which it's homogeneous, and you specify the pressure and the volume, always is at the same temperature. So we say that mathematically by saying that for a homogeneous fluid, a function of pressure, volume, and temperature must be 0. Or temperature is a function of pressure and volume. So that is called an equation of state, and the state of the system is completely determined by any of those 2 variables. So if I chose pressure and temperature, then it automatically implies a volume for a given mass. Now, then we're going to talk about a homogeneous solid. And in the absence of stresses, other than isotropic pressure, the equation of state for a solid, in the absence of stresses, is the same as it is for a fluid, solid, liquid or gas. It's not the same equation of state, but you have the same variables. If you have a homogeneous mixture of several compounds, like what? Who?
Air.
Yes, air. Air is a homogeneous mixture of nitrogen and oxygen principally, but also CO2 and argon and trace other molecules. A homogeneous mixture of several compounds, and variables are the temperature, the volume, the pressure, and the concentration of the different compounds. So if the concentration doesn't change, such as air, because nitrogen and oxygen, you don't think about them as reacting. Of course they do a little bit because there are traces of oxides of nitrogen. But if you don't, if you if you say the concentrations are the same, then for a homogeneous mixture like air, then it has a simple equation of state. Now, if you had a non-homogeneous fluid, which means that we might have two phases, a solid and a liquid and a vapor, or a solid and a liquid. The state is defined by the mass, the chemical composition, the state of aggregation, whether the aggregation is in very fine particles, because if they're very, very fine particles, you have energy on the surface that's significant. The state of aggregation, the pressure, the volume, and the temperature of each part. These variables are not independent. The total volume is the sum of the volumes of each part. And in each homogeneous part, the volume, pressure, and temperature for a given mass and chemical composition is connected by an equation of state. So that's the simple case without very finely divided phases. Now comes a very important idea in thermodynamics. What is an equilibrium state? An equilibrium state means that there is no change of state for no change in external conditions. And behind that statement is a very important idea, that within the state there are no currents, no motion, no heat being conducted from one part to another, no currents. So an equilibrium state would mean that the fluid inside a volume is at rest, and it is at uniform temperature throughout. There's no heat currents. Now comes the next idea in thermodynamics that I hope you're all familiar with, or most of you, and that's a reversible process. What's a reversible process? A reversible process is a transformation from one equilibrium state to another equilibrium state. So you take this volume and this temperature and you transfer it to a different volume and a different pressure, or the same pressure and a different temperature. So you transform it to through a sequence of equilibrium states. You never depart from equilibrium. So, for example, if you moved a piston very rapidly at a speed, say, greater than the molecular motion, the molecular speeds of the gas, if it were a gas, then you could move it so fast that the gas wouldn't follow it. And you'd have a non-uniform state behind it. Wouldn't be uniform. You'd have vacuum somewhere and different pressures and temperatures somewhere else. So a reversible process is a transformation from one equilibrium state to another through a sequence of equilibrium states. So that idea is that the process is quasi-static. That is, I can go from this static state to this one by a sequence of steps. And I can make them very small or slightly bigger, and I get the same answer. So it's quasi-static. It means that there's no dissipation, because if there's dissipation, there are currents, there are temperature changes. So there are no currents. It requires successive states of transformation to differ by infinitesimal amounts. So a reversible process just takes you infinitesimally from one state to the next state, and then to the next state, You don't do things rapidly by large-scale changes. Okay, so now what is thermodynamics? So thermodynamics basically establishes relationships between state variables, equations of state. And it also enables you to describe changes of state of a system due to outside influences, like, for example, doing work. So you might do work in all kinds of ways. You might move the piston very quickly, or you might move it very slowly. So there might be, you might do work by moving a piston, or you might be adding heat to change the state of a system. Okay, so now what are the laws of thermodynamics? And these were very painfully and experimentally discovered, and it's hard for you who just read it in textbooks to realize how big the disputes were about these laws. And the first of these laws, the first law of thermodynamics, says that the final internal energy minus the initial internal energy is the heat added to the system and the work done on the system. So that law has within it three new ideas. What are the ideas? Firstly, the first idea that's obvious is that there exists something called the internal energy, which is a function of the state of the system. So it's a function of pressure and temperature, the state of a system. So if I reach an equilibrium state, I have an equilibrium internal energy that's a function of the pressure and temperature. And it says that if I have this volume of air and I make it adiabatic so that it's inside a Dewar flask, and now I do work on this system, and I can do work in all kinds of ways. I could oscillate a piston inside. I could move the piston slowly. I could change it by many different paths. But it says that if I keep track of how much work I've done, and so you've got to be able to work out how much work you've done, but if I keep track of how much work I've done, then it doesn't, if I have the same amount of work done, but I do it in different ways, if I do it by different ways, it gives the same final state for the fluid. It says that the internal energy for the same W with Q is equal to 0, so there it is there, with Q equal to 0, E final minus E initial is the work done. Q equals 0. Or that the final state is the initial state plus the work done. And if I do the same amount of work, it doesn't matter what path I've taken it on. I can expand it quickly or slowly. I always get, if I do the same amount of work, I always get the same final state. Now that's an experimental observation. It took a long time for people to believe that. So there's another idea. Gives the same final state for the same initial state. And it's like dynamics for the kinetic energy. So you can change the kinetic energy of the system, and you can have a gravitational field. So you can have a force, a gravitational force that's acting, and it'll change the kinetic energy of the system. So it's like the kinetic energy. And it also has in it the idea of energy conservation. That's to say that the internal energy won't change if the right-hand side doesn't change. And it also has in it the idea of heat. And the idea is that heat is something that is energy in transit. It's not a property of state. I can change the state of a system by bringing something hot up against something that's cold, or bringing something cold up against something that's hot. So energy can flow, or heat can flow from the hotter body to the colder body. And that is energy in transit, because the internal energy is changed. So, I had that E final minus E initial is the heat supplied to the system plus W is the work done on the system. Now, sorry, well, that's the yes, the heat and the work done on the system. So the work done on the system, if I take a volume here and I do work on it, then I'm going to overcome the pressure, so I have to put a pressure, and I could change the volume, but the volume of the system will be less. If I do work on it, it'll shrink. So the amount of work that I do would be minus P dV. Or it's the force times the distance. So it's the pressure force times the area times the distance the force moves. So the pressure times the area times the distance delta S. And the area times delta S is delta V, is the volume change. So when I compress it, I change the volume of the system, and the work done is the force times the distance, and it would be where W. So Q is heat added to the system, and W is the work done on the system, i.e. minus P dV. dV is negative. So that says that if I make small changes, it says that dE is equal to dQ minus P dV for the work done on the system, or dQ is equal to dE plus P dV. Sometimes the first law is written like that. And typically you will remember that this has a stroke through it. What does that mean? Beg your pardon?
The enthalpy is saying it's the enthalpy?
No, it ain't the enthalpy. It absolutely ain't the enthalpy. Why do you put a stroke through it like that? Come on, some of you have done thermodynamics before. You have to know that that's been done in classes for you, I don't doubt. Why? Nobody knows. Good God. Just as well I'm doing it. It's because it's an input. It's not a perfect differential. That's to say that it doesn't depend on the state of the system. If I add heat, I don't change necessarily. I don't add something that changes the state of the system. I can add heat by different routes in different ways. And finish up at this.